Okay, so the one other thing we have to look at is actually a review from grade 11 physics, and it's the question, is the collision elastic or inelastic? Now, if you remember from grade 11, elastic and inelastic involves two things. The first thing it involves is, let me do an example. Draw out an example first, and then I'll talk about what it involves. So imagine you have a 6 kilogram ball initially going 7 meters per second, and it runs into a 4 kilogram ball initially at rest. After the collision, the 6 kilogram ball goes off at an angle of, let's say, 36.87 degrees. And its final speed, so V1 final, is 4 meters per second. So you can pretty much bet that ball 2 is going to go up this way. Because remember, and we don't know what V2F is, or theta 2. How do I know it's going to go up that way? Well, remember, it has to be conservation of momentum. And so ball 1 has some momentum going down in the y direction. So ball 2 has to have some momentum going up in the y direction to cancel it out. Because initially there was no momentum in the y direction. Ball 1 was only moving in the x. So that's why I know if one goes down, the other's going to go up. So, but the question is it elastic? So back in grade 11, we learned that momentum is always conserved. Okay? So both in elastic and inelastic collisions, momentum is conserved. Okay? That's a given. The one that isn't always conserved is kinetic energy. Sometimes kinetic energy can be lost to sound, to deforming the object, etc. And sometimes it can be conserved. If it is conserved, then the collision is said to be elastic. So for an elastic collision, both momentum and kinetic energy are conserved. Okay, so both momentum and kinetic energy. But for inelastic collisions, momentum is still conserved because it always is. It's a law. But kinetic energy is not. Okay? And so when we do these problems, just like we did in grade 11, we use momentum to figure out the missing velocity. And then once we have the missing velocity, then we use the kinetic energy equation to find out if it's elastic or not. So we start off by first doing the x direction. And so we do m1v1 initial x plus m2v2 initial x is equal to m1v1 final x plus m2v2 final x. M2 initial is 0. We're looking for v2fx. So we're going to bring this term over. So v2fx will equal m1v1 initial, and I can drop the x because it's only in the x direction, minus m1v1fx, which is going to be the adjacent side of this right angle triangle, so it's going to be cos theta 1. And I'm going to divide by m2. So v2fx will equal m1 was 6 kilograms, v1 7 meters per second, minus 6 kilograms, 4 meters per second, cos of 36.87. And then I'm going to divide by 4 kilograms. And so I get a v2fx to be 5.7 meters per second. Okay, so that's my v2fx. Now I need to do my v2fy, so I do the y direction. m1v1 initial y, m2v2 initial y will equal m1v1 final y plus m2v2 final y. These both go to 0 because initially m2 is not moving at all and m1's only moving in the x direction. So it'll become minus m1v1f, and it is the opposite side, it's sine theta, is equal to m2v2fy. So v2fy will equal negative m1v1f sine theta over m2. So 6 kilograms, 4 meters per second, sine of 36.87 divided by 4 kilograms. V2Fy is equal to, oh, and there, I lost the negative there, negative 3.6 meters per second. And the negative just means opposite number 1. Number 1 was going down, so number 2 is going up. So we can get our V2F now. This is 5.7 meters per second, and this is 3.6 meters per second. So I can square them, add them together, take the square root, and when I do, I get 6.74 meters per second, and I can find the angle, and when I find the angle, it is 32.276. 32.276 degrees. So V2F is 6.74 meters per second at 32.276, oops, there is a decimal there, degrees, and it's CCW, counterclockwise from the original. Okay, so that's my V2F, which we've been finding now for a couple of days. But now it wants to know, is it elastic? So to find out if it's elastic, we have to use the conservation of kinetic energy equation from grade 11. So the kinetic energy of the first one initially, 1/2 m1v1 initial squared, plus the kinetic energy of the second one initially, should be equal to the kinetic energy of the first one after the collision, plus the kinetic energy of the second one after the collision. Remember, energy is a scalar, so we don't have to do it in the x and the y, we just do one shot. Initially this goes to 0, so 1/2 6 kilograms times 7 meters per second squared, and remember it's just the 7 that gets squared, equals 1/2 6 kilograms 4 meters per second squared, plus 1/2 4 kilograms 6.74 meters per second squared. 49 times 3, so this is going to be 147 kilogram meter squared per second squared is a Newton meter or a joule. Remember, energy is measured in joules. 16 times 3 is 48 joules, and 6.7, I'm going to cheat on that one, it's 90.9 joules. And so we have 147 joules initially, and we have 138.9 joules finally. So they are not equal. So remember how you put a line through the equal sign and you write inelastic. And remember that either they'll be equal to each other or the initial will be bigger. The final should never be bigger. If it is, you screwed it up, because you should never be able to make kinetic energy as a result of a collision. If you could, you'd get really rich and remember your physics teacher. Okay, so it's always going to be either equal or the final's going to be smaller. Now, there's a couple of questions that come along and say, how much kinetic energy was lost? Well, to find out how much was lost, then you would just subtract the final from the initial. So in this case, there would be 8.1 joules lost if the question were to ask that. Okay, so now for homework, I would like you to do page 513, number 38, and from the worksheet, numbers, I think I missed something. Numbers 1 to 4, I might change that. I'll let you know in the class notes. Okay? Thanks.